This video is about LC filtering for the Class D power amplifier driving a loudspeaker. And it corresponds to section 35.4 of Applied Analog Electronics. We've been looking previously at RC filters, but we haven't looked at LC filters before. And the reason we don't use an RC filter for this application is that we're putting a lot of power out to the loudspeaker. And we don't want to lose a lot of that power being dissipated in a resistor. If we did RC filtering, it is possible to do that, but then you need very large power resistors, and a lot of the power that comes out of your amplifier goes into heating up that resistor rather than being delivered as power to the loudspeaker, which kind of defeats the purpose of having the high efficiency Class D amplifier. So why are we doing a filter in the first place, actually? It's to get rid of a lot of that pulse modulation, the high frequency square wave that we had there, because that high frequency waveform, though it's not going to cause the loudspeaker to do anything particularly interesting, it causes electromagnetic interference, radiation in the radio frequency range, because our pulse width modulation signal is going to be well above the audio range, needs to be in order for the Nyquist frequency to be in the audio range, or to allow the audio range through to be less than half the PWM. And the sharp edges of that rectangular signal has a lot of harmonics, so you end up with a lot of radio frequency energy in the waveform. And we want to filter that before we run it through the long wires to the loudspeaker, because those long wires are going to act as antennas and broadcast that radio frequency interference. So we want to filter out those high frequencies, the PWM frequency and the stuff above it, without reducing the audio frequencies that we want going to the loudspeakers. Okay, and the reason for using the LC filter rather than RC filter is that we can get much better power efficiency. We don't dissipate a lot of energy in our filter. It almost all goes to the loudspeaker. So what does an LC filter look like? Well, the filter we'll be using basically consists of an inductor and a capacitor. And this will be driving our loudspeaker. Now there's two things we want to do here. One is I want to give you a basic feel for what an LC filter does when it doesn't have any load, just the simplest version of an LC filter. And then I want to look at how we're actually going to model it with the loudspeaker, because this loudspeaker here has an impedance, fairly complicated impedance. You modeled that in Lab 8. And so putting it in parallel with a capacitor here gives you an even more complicated impedance. And so to model this thing is not really something you want to do in your head. This is something you want a computer to do for you. And so we're going to use GNU-plot to do this modeling for us, to look at how much power do we deliver to the loudspeaker with a filter like this one. But let's first look at a much simpler filter, just to get a feel for what we should be seeing and how what we actually get varies from that. So basically, let's take a look at the simplest LC filter. No load, just an inductor and a capacitor. It's just a voltage divider. All we need to know is the impedances of these things. Impedance on the bottom here, 1 over j omega c. And then the combined is 1 over j omega c plus j omega l. That looked kind of messy, but it's really easy to simplify, multiply top and bottom by j omega c. And that gives us 1 over 1 minus omega squared LC. And that's kind of cool. It's a purely real function. There's no imaginary component here. What comes out is in phase with what goes in. And it's got an interesting thing here. When omega is equal to 1 over square root LC, this bottom part here goes to 0. So the gain of this LC filter becomes infinite when omega is 1 over square root LC. That's a resonance. That's a big resonance. And let's take a look at that with GNU-plot and see what the curve looks like. Okay, so I am going to switch over to a little GNU-plot script here. I'm going to load definitions.GNU plot, so I have all my usual formulas for voltage dividers and impedances of inductors and impedances of capacitors, all that stuff. And I'm going to write a gain equation here. I'm going to do a voltage divider. Here I put a resistor in series with the inductor because real inductors always have a series resistance sort of built into them because of the resistance of the wire. And I have the capacitor on the bottom. And here I've got the inductor that I picked, 100 microhenries. That's a reasonable sort of size for an inductor. And 2.2 microfarads, again, a reasonable sort of size for a capacitor. I made the resistance 0 here, so we are looking at just that LC voltage divider circuit. And I'm going to plot the absolute value of the gain of this thing as a function of frequency. And there it is. What we see here is at low frequencies, the gain is 1. At the resonant frequency, it goes up to infinity. Now, GNU plot, of course, can't get to infinity. Depending exactly where it samples, how close to the resonant frequency it samples, it will get up to some large value. And the more samples you put in here, the closer it'll get to the resonant frequency and the higher this value will be. Here it gets up to about 1,000, but the underlying mathematical model that it's trying to compute actually does have a going all the way up to infinity. And then in the high frequency range here, we have it dropping off. But it's dropping off much faster than we're used to seeing for RC filters. If you look at this thing, it is dropping off 2 decades per decade. So that's because if we go back to looking at our formula here, there's an omega squared down here. When omega is large, and the 1 doesn't matter, we have 1 over omega squared LC. So this thing is dropping as the square of the frequency, not just with the frequency. Okay, so this is all fairly simple, but now let's take a look at what happens if we put the resistor in. What should it be doing? Well, it's a very small resistor, so you'd think it's not going to affect much, but it does have some effect. So let's go back over here. Let's say 0.2 ohms, which is sort of what you might expect for a 100 microhenry inductor. All right, so save that and rerun GNU plot. And notice now that the spikes, the sampling in the same places as before, this spike doesn't go up to 1,000, it only goes up to maybe 30. So, but the curve otherwise looks very much the same. So putting in that small amount of resistance really damps the resonant peak. And this is something that we're going to be wanting to play with because that resonant peak is not something you usually want in your filter. You want that flat part at the beginning there, you want the rapid drop off, but you don't want a huge resonant spike here. And so we'll be playing around a little bit with different inductors, different capacitors, different places where power might get dissipated in order to try and keep that spike small enough that it doesn't disturb the behavior of our circuit any more than it has to. Okay, let's take a look now at what we're actually wanting to model, because what we had here was a pure inductor and capacitor, or inductor with series resistance and a capacitor, but we had no loudspeaker in here. And the loudspeaker is an impedance. It is going to affect things. So here's a more realistic view of what we want to do. We've got the inductor with a series resistance there at the top. We've got the capacitor. And here I picked a particular inductor. You're going to have a fairly small number of choices for inductor. And so you'll want to, for each inductor, plug it in and see what values of capacitors you could choose and see if any of them would work for you. And then I've got a model here for the loudspeaker. And this model should look familiar to you. It's the same sort of model as you had in Lab 8. But here I've modeled a different loudspeaker than the ones you'll be using. Because the loudspeaker that I have here is something called a puck. It's a bass shaker for shaking furniture. It's got a very low resonant frequency. It's not designed for producing sound, but vibration in furniture. So the sort of thing you put in a gamer's chair. and the parameters here are not the parameters that would be appropriate for your loudspeaker. So you'll be wanting to do the same thing that I'm doing here, but with different parameters, with parameters that match the loudspeaker that you have. Okay, so what do we do this? Well, obviously, we're going to want to use a script. So let's turn off. All right. So this script is one that's in the book, and it's available to you to download. And I'll walk you through it now to explain what the script is going to do for you. First, it loads definitions.gnu plot. So we have a bunch of definitions there. What a voltage divider is, formula for impedance of inductor, formula for impedance of a capacitor. Also, there's a formula for real power. We talked about real power earlier. You're not going to have to actually write out all the formulas for it, because there's a formula there in definitions.gnu plot that you can just use that says, give me a voltage and give me an impedance, and I'll tell you what the real power is for that voltage driving that impedance. You have to give it a frequency too, of course, because the impedance depends on frequency. Okay, so here's our loudspeaker model, and it's just the model from Lab 8. It's a resistor in series with the nonlinear inductor-like thing. And then in parallel, a resistor, an inductor, and a capacitor for the mechanical resonance. And I have a bunch of parameters set here. You probably have a very similar design for the model for your loudspeaker, but very different parameters. At least I hope they're different. You probably should not be trying to use a puck as your main output device for your power amplifier. Okay, here I've got an optional thing, choosing a series resistor. That's if you plan to measure your loudspeaker current as part of your experiment, your lab setup. If you want to measure the loudspeaker current, you'll need a sense resistor. How big is that sense resistor? Maybe half an ohm, maybe an ohm. And if you do that, you'll want to model it, because it's going to change the impedance of your loudspeaker. So I've put that model in here, but I set it to 0 under the assumption that you don't have a series resistance here for measuring the current through the loudspeaker. And then I've got, well, what is the power that goes into the loudspeaker if I don't have any filter? And basically it's just saying, well, what's the real power? And then I compute the voltage at the loudspeaker. And to do that, I've got a voltage divider, which is the series resistors and the loudspeaker. Multiply that voltage divider times the input voltage, and then use the loudspeaker impedance as the impedance for the real power function. So that's the power we deliver to the loudspeaker if we just hooked the output of the power amplifier directly to the loudspeaker. Okay, and then I've got a filter model. And the LC filter here, I've got two things. I've got the loudspeaker model, and I've got the filter impedance and resistance, or the inductance, resistance, and capacitance for the filter. And so it's just a voltage divider. The gain of this thing is just a voltage divider for the inductor and resistor on the top leg, and in parallel the loudspeaker plus the series resistor, that in parallel with the capacitor. So that's the circuit we saw just a moment ago. This one. Okay, so I just took that that design and put it into GNU plot as a voltage divider. And now I've got a couple different values here, and I'm going to take out this comment here. So the top line is a 3.3 millihenry inductor. The second line, which replaces the first one essentially, is for 330 microhenries. And these are both the parameters from a particular series of inductors that are cheap to buy. I happen to have the 330 microhenry ones. I don't have the 3.3 millihenry ones. I never bought that one. Now I've got, what I want to plot though isn't gain, and it isn't voltage. What I want to plot is, what is the real power being delivered to the loudspeaker? What is the loudspeaker's output going to be? And that basically depends on what's the power into it, and some on how efficient it is at coupling that into vibrations of the air. I'm not going to model the vibrations of the air, but we will model the real power into the loudspeaker at each frequency. So the loudspeaker power is the real power. I'm going to take the voltage of my signal, the gain of the filter, and then that voltage divider for if I've got a series resistor, just how much of that is going to the loudspeaker, how much of the voltage is going to the loudspeaker rather than to the resistor. And then finally the impedance of the loudspeaker. And I also have here total impedance, if for some reason you want to see that, but mostly you're not going to care about that. It's available for you if you want to compute it. And you have to choose your power supply voltage, because that's going to determine how much power you can deliver your loudspeaker. And I put in 10 volts here. Again, you do not want to use 10 volts because some of your components cannot handle 10 volt power. Put 10 volts into them, you get magic smoke coming out, and that's not going to be good, particularly if you're doing this at home and don't have any spares. So pick a power supply voltage that's more reasonable and put it here. So computing with the power supply you're actually using. The RMS voltage you're going to get if you have a sine wave that goes coming out of an H bridge that's for your power supply is going to be square root of 2 times the amplitude of, and the amplitude is what's going to come from the power supply. This is again assuming you're using an H bridge to create the sine wave. And then I've got something here for the peak power frequency. Now this is just used for computing one sort of illustrative line on the plot, the half power line, and it's not, the 32.3 here is again totally the wrong number for you. This is what I got for the puck in what I was doing, and I'll show you in a moment how you get this for your loudspeaker. It's done by doing a plot and then looking at the plot and picking a point on the plot. The half power is half of the power of the loudspeaker at the peak power frequency. All right. So what do we do here? All right, I just have title, range, label, all this stuff is sort of normal. And then I'm going to plot out that half power line. The reason for that is to show where the power drops from half of what it is in the pass band, because those are that gives you the bandwidth for your filter. And generally people look at where is the output power within a factor of 2 of the maximum power. I'm going to plot the power I would get if I didn't deliver, if I just put it all through the loudspeaker, didn't have any filter. And then I'm going to do the filter, and maybe I need to move a little bit out of the way here so you can see all this. I'm going to do the filter with various different capacitors, 10 microfarads, 4.7 microfarads, 2.2 microfarads, and so on. And the idea is I've picked a particular inductor up above there, and I'm picking various capacitors. Pick capacitors you've got, and take a look at what the effect is of each one. So let's run this and see what we get. Oops, that does not look right. I didn't save the file. There. Okay, this is now with the 330 microhenry inductor. And with the 330 microhenry inductor, we get tall spikes here at the resonant frequencies. That's because there's very little resistance here. We're not getting much damping of that resonant spike. And this is a bit of a problem, because what happens if we play sound through this thing is that we will hear a buzz at the frequencies of these spikes, and that would be quite unpleasant. So I would regard none of these designs as acceptable designs. The peak power here is about here on the curve, so just looking at the no filter curve, the green curve here, you can see that that one doesn't have any resonance because there's no filter, and it's just showing that the power drops as we go to higher frequencies. And that's because we've got an inductor-like, that sort of weird inductor-like behavior there. We also have a dip here in the power delivered to the loudspeaker right at the resonance, at the mechanical resonance. So what I did for picking, remember there was this, where's the peak power frequency? I did that by looking at the no filter one and trying to figure out where is the peak in this region. And I've got something around 32 hertz. You're going to want to do the same thing, looking at the no filter power for your loudspeaker and saying, well, where is that peak power there? And then it draws the line here at half of that peak power. And so we've got a half power is about 1.53 watts. The peak power is about 3 watts, which is, you know, a decent amount of power to putting into the puck. If we look at the other filters, notice that in most of this range, out to about here, all these things are behaving the same. You're not getting any real change to what's going in this. If you think of this as the audio range, it's up to about, what, 900 hertz here. In that range, the filter isn't really changing anything. And that's what we expected, because remember that the filter for an LC filter was 1 for low frequencies. The gain was 1, there's no change. Once we get to the spike, we got that nasty resonance, but then it drops very, very rapidly. It's dropping here faster than with the square frequency, because we have some drop due to the loudspeaker itself, and then additional drop due to the LC filtering. And so if our PWM frequency here is anything reasonable, 50 kilohertz, 100 kilohertz, we have lots of curves here where we're down to delivering, you know, microwatts, tens or hundreds of microwatts to the loudspeaker at those frequencies, which is negligible. We're really getting very, very little power going through at the high frequencies, going through the wires. So we're not going to get radio frequency interference. But those resonance spikes, I hate them. And this is why I went back. Let's expose this again. Let's go back and look at those inductors. I had here been using the 330 microhenry inductor. Let's comment that one out so it exposes the 3.3 millihenry inductor. Save the file this time and run that and take a look at it. And now, because this inductor has a much larger internal resistance, 3.7 ohms instead of 0.3 ohms, we have got much, much less in the resonance spikes. Those are rounded humps now rather than those big spikes shooting way up. But our peak power is much smaller. We're only getting about 2 watts to the loudspeaker. We're dissipating probably a watt in that big inductor. So let's hope that it can handle that current. Another calculation you might have to do is to look at, well, what's the current going through the inductor, and is it within the specs for the particular inductor you have chosen. Here we're getting about 2 watts at the peak to the loudspeaker. But now we've got some curves there where we can actually, the blue curve and the orange curve, the first two there, they actually stay above that half power point much longer than even the loudspeaker without a filter does. That resonant spike there is actually raising the energy being delivered to the loudspeaker to the point where it's still usable up to a higher frequency. The light blue one looks like it gets to the half power point at about 430 hertz, whereas with without the filter we got about there too, because without the filter we had getting to the 1 watt point is later because we're starting at 3 watts. So for the no filter curve, we're looking at this thing. It's a little bit misleading because the half power point is earlier. It comes about where all the other lines are sort of clumped together and crossing, and those are at about 470 hertz. So that's about where the half power point is. With the blue one, we get up to about 1300 hertz. And with the orange one, we're all the way up at about 1800 hertz. So we're getting maybe 4 times the bandwidth by putting in the filter. We're losing stuff in the audio range, power is being dissipated in the filter, but we're maintaining a more constant power to the loudspeaker up to about 1800 hertz. Once we get beyond that, then we're starting to get to the point where we're no longer getting the high bandwidth to the loudspeaker because the spike in frequency is coming too late, and we've already gotten below the half power point before the spike pulls it back up. So I would say that the yellow, blue, red, black, and purple curves aren't nearly as good at designs here because they won't be suppressing the PWM frequency as much as the light blue or the orange curves do. Because if you look at a high frequency like, say, 50 kilohertz, the light blue curve is way, way down. It's way off the bottom of the graph here, whereas the purple one is just barely getting down to the 100 microwatt level. So we're getting much better suppression of the high frequencies from the first couple curves, and we're getting wider bandwidth. So those are clearly superior designs. Now there is some question about whether the no filter design is a better one, because there we don't lose any power for the filter, they're not being a filter, but we have a huge amount of energy still at the high frequencies which is not being suppressed. And so there's a trade-off. How much do we need power delivered to the loudspeaker versus how much do we need to suppress the radio frequency interference? But of the ones with the filter, the first two here look like much better designs than the later ones. So it looks like the 10 microfarad or the 4.7 microfarad designs look quite reasonable. 2.2, not so great. And once you get down to the really tiny capacitors, they're really not doing a thing for you. Okay. So far we've been talking all about design with a single inductor, a single capacitor, and the loudspeaker. But there is another design you might want to look at. And that is to put an inductor on each of the two legs. And the reason for that is that if you now make the long wires out to the loudspeaker, so you have the inductors and the capacitors inside your amplifier box, and then you have long wires running out to the loudspeaker, it's those long wires that you don't want to have radiating radio frequency interference. And the radiation is not just between the two wires, but of those wires with respect to earth ground, because we're looking at radio transmissions. Earth ground actually matters now for things. By putting the inductors on both sides, you're going to be filtering both sides with respect to earth ground, and so you get less radiation. This design with the inductors on both sides, the sort of symmetric design, looks nicer. You can use exactly the same script to deal with it. It's just that those two inductors and the series resistors that correspond to the inductors have to be added together for the script to be modeling it correctly. Because we still have a voltage divider here, and the part that's on the loudspeaker, the part that's here in the middle, is in series with two inductors, two resistors. And so if you add those inductances and resistance together, you'll still model what is going to the loudspeaker using exactly the same math as we've been doing, just not using a single inductor, but the two inductors added together as the input to the script. And that's basically all you really need to know about LC filters in order to do your power amplifier design. So that's it for now.